Students, in this video we are going to discuss about transient analysis of RL circuit. So here is a circuit that I have taken, a simple RL circuit with resistance R and inductor L connected in series with the DC excitation V into U of t. This U of t is nothing but a step function. The amplitude of the step function, unit step function, is 1 for time t greater than or equal to 0. So if you are going to take a 5 volt supply, 5 into u of t is nothing but 5 into 1, which is equal to 5, but the amplitude exists only for time t greater than or equal to 0. So that is the interpretation of this v into u of t, and you can see a switch here. Let me mark the positions of the switch. This is position 1 and this is position 2. So the switch is in the position 2 for longer time, and we are assuming that there is no initial energy stored in this inductor, which means that there is no initial current flowing in this inductor. Now I am going to close the switch at time t is equal to 0. I am going to close the switch to position 1. So when I close the switch to the position 1, the loop is closed, okay, and now you will have a current flowing in the circuit. Let me take that current to be I of t. Because of this current, you will have a voltage drop across resistor. Let me term it as VR of t, and the voltage drop across inductor as VL of t. So when you apply Kirchhoff's voltage law to this closed loop, you can write the differential equation governing this particular loop. So Kirchhoff's voltage law states that voltage drop across this resistance and across this inductance is equal to the input excitation V into U of t. So let me write the differential equation. It is R into I of t plus L into di of t by dt, which is nothing but voltage drop across the inductor, is equal to input V into U of t. So this is the differential equation governing your closed loop, and now you have got to apply Laplace transformation to this uh, differential equation. Students should be very much familiar with this Laplace transformation. Only when you apply Laplace transformation, it becomes easy for you to solve differential equations. So now I am going to apply Laplace transformation of I of t is nothing but I of s. R is a constant, so I am writing R as such, plus L is a constant. Laplace transformation of di by dt, differentiation of the variable, is nothing but s into I of s, capital I of s, minus small I of 0. This small I of 0 is nothing but initial current through the inductor, and it is equal to V is constant, and Laplace transformation of U of t is 1 by s. So now there is no initial current. That is what is our assumption initially. So now this I of 0 is going to be 0 because we have taken no initial current through this inductor. Okay, so I of 0 is equal to 0. Now if I rewrite this function I of s, I will get it as I of s is equal to V divided by s into SL plus R. Let me take L out so that I get it as in a standard format, that is V by L divided by S into S plus R by L. So in the denominator I have two terms, one is S and another one is S plus R by L. So now I am going to apply partial fractions to this function I of s, so that I can split this V by L divided by S into S plus R by L into sum of two simple functions, so that it is easy for me to apply inverse Laplace transformation. So let me apply partial fractions. So if I apply partial fractions, then I get it as V by L divided by S into S plus R by L is equal to A by S plus B by S plus R by L. So we can get the value of A is equal to the given function into the denominator of A at the denominator should be equated to 0, then you get the value of S at S is equal to 0. So this is how you find the value of A. A is equal to, here you can see this SS gets cancelled, and when S tends to 0 this becomes 0, so this also goes off, and V by L divided by R by L is nothing but L gets cancelled and you get V by R. Similarly, B is also got by the given function, that is V by L divided by S into S plus R by L into the denominator function of the B, that is into S plus R by L, and at you get the S value by equating the denominator to 0, that is S is equal to minus R by L. So here these two functions get cancelled, and when you substitute S is equal to minus R by L here, L will get cancelled and you will get B to be minus V by R. Students can either use this method or they can use a method like cross multiplying this term and then equating the S coefficients and constants to get the value of A and B. Any method the student can use to find the value of A and B here. So I have used like this. So after getting this A and B values, so now I am going to apply A and B here to obtain this I of S. I of S, this is nothing but I of S. So I of S has been split into these two terms. So now I of S is equal to A is nothing but V by R divided by S plus minus V by R is the value of B divided by S plus R by L. Now we have got to apply inverse Laplace transformation so that we get I of t. So apply inverse Laplace transformation to this equation. So inverse Laplace transformation of I of S is I of t, and this V by R is a constant. Inverse Laplace transformation of 1 by S is nothing but 1 into U of t, that is U of t. I will write it U of t minus V by R is a constant, and inverse Laplace transformation of 1 by S plus R by L, that is 1 by S plus A. This is, let me take this as a constant A. It is nothing but e power minus AT, that is R by L into T into U of t. So I of t is nothing but V by R. The amplitude of U of t is 1. So 1 minus e power minus R by L into t. U of t amplitude is 1, but the amplitude exists only for time t greater than 0. So I will write I of t is equal to V by R into 1 minus e power minus R by L into t for t greater than or equal to 0. So the equation for I of t can be written either like this or like this. So I have just removed I of t and I have stated that it is for t greater than or equal to 0. So this is my equation of current, that is flowing in this particular closed loop when the supply is connected to the RL series circuit. Let us check what is the value of the current at time t is equal to 0 At time t is equal to 0, if I substitute 0 here, I of 0 is nothing but anything power 0 becomes at time 0, so anything power 0 becomes 1, 1 minus 1 becomes 0, so I of 0 is equal to 0. So at time t is equal to 0, the current here is nothing but 0. I of 0 is equal to 0. At time t is equal to infinity, you can see that at time t is equal to infinity, I of infinity, anything per minus infinity is 0. So 1 minus 0 is 1. So you get it as V by R. So the steady state, okay, at time t is equal to infinity, the steady state is reached. The steady state current is given by V by R. Uh, Let me give the variable name for steady state current as I. So I is nothing but V by R, which is nothing but steady state current. So the current equation I of t is nothing but V by R is capital I into 1 minus e power minus R by L into t for time t greater than or equal to 0. Now let me find the voltage across resistor. VR of t is nothing but I of t into R. So this I of t into R will give you the voltage across the resistor. So VR of t is nothing but this function I of t into R. So I into R 1 minus e power minus R by L into t. So we know that I is equal to V by R. So IR is equal to V into 1 minus e power minus R by L into t. So let us find now the voltage across this inductor. So VR of t plus VL of t is equal to this constant V, isn't it? So now just to substitute this VR of t here, that is equation number 2 here, you get it as VL of t is equal to V minus V into 1 minus e power minus R by L into t. So VL of t is equal to V into e power minus R by L into t. So let me take this equation as equation number 3. So here I have drawn all the three variables, that is the current through this entire loop I of t. This I of t function is equal to I of t is equal to capital I into 1 minus e power minus R by L into t. But now I have taken this capital T, which is nothing but time constant. T is equal to L by R. This L by R is called as the time constant. So I am replacing where all I got this R by L with the time constant. So time constant is equal to L by R. So it is e power minus t by capital T. So you can see that the current is exponentially increasing and it goes to the constant value capital I at time t tends to infinity. So that is the interpretation. So this I of t, we have drawn it here. It increases exponentially, and when this time t tends to infinity, what happens? E power minus infinity is 0. So I of t is equal to constant I. So at time t is equal to small t is equal to infinity, this current will reach the constant current value, that is capital I, which is called as the steady state current. Now here you can see that the voltage across the resistance, this equation, and the voltage across the inductor, this equation, both are pictorially shown here. Voltage across resistance exponentially increases according to this equation, and voltage across inductor decreases exponentially according to this equation. At time t is equal to infinity, here when I substitute time t tends to infinity, anything per minus infinity becomes 0. So this voltage across the inductor will become 0, which means that at time t tending to infinity, the inductor will behave as a short circuit. At time t is equal to infinity, inductor becomes or behaves like a short circuit. Behaves like short circuit. This is one of the important inference. At time t is equal to infinity, here you can see that the constant current only I is equal to V by R flows. That means that this inductor is behaving as a short circuit. So when this inductor becomes a short circuit, now you can see the constant current will be only just V by R flowing in this circuit. Now let me substitute this small t is equal to time constant capital T. Let me see what happens. So this when time t is equal to the time constant time capital T, then your I of t is equation becomes I of t is equal to capital I into 1 minus e power minus t by t. Okay. So e power minus 1 is nothing but I of t is equal to 0.632 into I. So I have computed e power minus 1 and 1 minus e power minus 1. I get it as 0.632 into capital I. So the inference here is your current I of t reaches 63.2 percentage of your steady state current when the time is nothing but equal to time constant time. So when you come to a point when t is equal to capital T, for example, if this is the capital T time, the current will be the current will be 0.632 I. That is the inference. That is 63.2 percentage of your steady state current. Or rather, I can say that the time taken by the current to rise to 63.2 percentage of the steady state current is what is the time constant T. Okay, so the time constant T is nothing but the time taken by the current to reach 63.2 percentage of your steady state current. One more inference you can make from this graph: at time t is equal to 0, the current is 0. So immediately after closing the switch, the current through this loop is 0. So which means that this inductor is acting as a open circuit at time t is equal to 0 plus, that is immediately after closing the switch, the inductor is acting as a open circuit, that is at time t is equal to 0 plus, that is immediately after closing the switch, that is after connecting the supply to the circuit, inductor behaves like open circuit. So that's why there is no current flowing, and the current slowly increases and reaches its steady state value at time t is equal to infinity. So when time t is equal to infinity, the inductor behaves as a short circuit. So this is the behavior of the inductor in the transients. In this case, because the current is rising exponentially, this case is called as rise of current case. So in the next video, we will see another case where the circuit is disconnected from the supply, which will be called as decay of current case. That will be discussed in the next video.